Hello, Chem students. We're going to have another day where we're going to spend a very brief period of time talking about a topic that may have some degree of familiarity to you. And then by the end, we're going to introduce a concept and idea that might be a little more challenging or difficult, or actually just very different than what you've dealt with. So we ultimately want to, by the end of this video, to be able to make a conclusion about the physical properties of water by describing phase changes. We're going to talk about phase changes in this video. And think about it on a microscopic / nanoscopic level. We're talking about an atomic level or molecular level, and how that might have an impact on different physical properties of water in the natural world. So let's start with states of matter and changing between states. Again, the next few slides should be painfully obvious, but we're going to go through it anyway just to get to the heating part. So when you're talking about states of matter, there are three main ones. There's solid, liquid, and gas. And you learned in very, very early years that solids were things that were hard, liquids you could pour, and gases were the airy type things that are around you. And I'm not saying that's untrue, but there's a more sciencey way to remember them. So first thing, solids. In general, solids, if you're looking for whether something's a solid is going to have a definite shape and a definite volume. It's not going to change shape and it's not going to change volume. You can do what you need to it. It's still going to have the same shape and the same volume. You break it in half, that means you're going to have a different shape, but that's a physical change. If you have a brick, a solid piece of material, that is going to have a shape and is going to have a volume. They have mass because they are matter, and they take up space because they're matter. Particles in a solid are very, very close together. They vibrate very, very little, very, very, very mild vibrations. They're packed together very, very tightly, and they possess little energy. Not as in no energy. Whatever you're watching this video on, the casing of your laptop or your phone, whatever, it is probably made out of plastic or metal. It has molecules in it, and those molecules are vibrating as you speak. There's a little bit of energy, but it has a very small amount of energy. And they vibrate in place in a very organized structure. Then there's liquids. Liquids are a little more interesting. They take the shape of whatever container they're put into. So they have an indefinite shape, but they have a definite volume. If I take a 2-liter bottle of soda and pour it into a pitcher, it's still going to read 2 liters. Okay, no matter what container I put it in, it's going to read 2 liters. I take a 2-liter bottle of soda and pour it into a beaker, it's going to read 2 liters. The volume is the same. The shape it takes is going to change. They have mass and they have space, therefore they are matter. Particles of a liquid, they're pretty disorganized, but right on top of one another. They're very, very close to one another, but they're very disorganized. There is no real pattern to their arrangement. They're loosely packed together. They have low to medium energy. They're not really super aggressive, and they flow around each other, whereas the solids stay pretty much in place. They don't move hardly at all. One of the reasons why liquids do take the shape of the container is they can slide past one another very, very readily. And then there's the gases. Gases are the crazy ones. Gases spread whatever container they're in and don't have a definite volume. You can compress them, you can expand them, you can allow them to flow freely. Gases do whatever they want. They have an indefinite shape and an indefinite volume. But they have mass and they have space, so they are matter. Particles of a gas, they're bouncing off one another, they're very, very far apart, and they're just flying along, but they are very, very tiny, and there's huge distances between them. They do whatever they want, they move very, very fast, they have tons of energy. If you look at the solids being very, very low and liquids being pretty low, gases are off the charts, super high amounts of energy. And then finally, finally, there's states of matter. Okay, talk about the different states of matter. There's liquids, gases, solids, plasmas, which you didn't talk about. Mixtures are not necessarily states of matter. I think they just were being cute. What would it take for matter to move from one state to another? What do you do? How do you move matter from one state to another? How do you go from a solid to a liquid, or a liquid to a gas, or a gas to a plasma? The answer is energy. If you add energy to a solid, it turns into a liquid. If you add energy to a liquid, it turns into a gas. Remember, solids have the least amount of energy. Liquids have a little bit more than that, and gases are through the roof. So you can add energy and change phases. When added energy is added, the particles move faster. So the solid particles which barely move become the liquid particles which move more, that become the gas particles that move crazy. When energy is taken away, they're going to slow down. When you have that steam that you allow to condense to turn into liquid, you lose energy. And when that liquid goes into the freezer and turns into a solid, then it loses even more energy. So a solid plus energy, you get a liquid. When the energy is added to the solid, it becomes a liquid. When a liquid has energy added, it becomes a gas. When energy is added to liquids, it becomes a gas. So the norm is a solid you add energy becomes liquid, a liquid add energy becomes gas, and vice versa. When you remove the energy, it goes backwards. So what you have here is called a phase change. And in Chem 2, we're going to use a whole lot more time to address how this whole thing comes together. But this is an example of a phase change diagram. Notice at the very, very bottom at temperatures, this happens to be one for water. At temperatures below 0 degrees, it is going to be a solid. It's going to be ice, solid ice. But at 0 degrees, as you add energy across the bottom, the phase change takes place. And while the phase change is taking place, the temperature does not change. While the phase change takes place, while you're melting ice, your water does not change temperature. Classic example, you have a nice summer day and you have a glass of your cool beverage, but you have a lot of ice in there. That beverage stays cold until all the ice is gone. As long as the solid ice is in the beverage with the liquid water, it's going to stay very close to 0 degrees Celsius or 32 degrees Fahrenheit. But as soon as the last energy that goes into that container from the outside goes into that container and stops going towards melting the ice, then immediately all the energy goes in is going to go towards increasing the temperature of your water until you get to the point where your water is boiling. Okay, so when you have that glass of liquid, it's going to get the room temperature. Is what's going to happen. So if room temperature happens to be 25 degrees, 35 degrees because it's hot, super crazy hot because 35 degrees is like 100 degrees, then you're going to get up to here. But suppose you put that on the stove and you keep adding, it's going to get warmer and warmer and warmer until it gets to the boiling point. And again, during the boiling of water, the temperature stays constant. You can crank up that stove all the way to the max. It's not going to make the water any hotter. It's still going to boil at only 100 degrees Celsius. And once all the water has evaporated away, then the energy you put into it, if you have the ability to put energy into it, will go towards making the steam hotter and hotter and hotter. So during these flat portions of the graph, during the melting and during the phasing, the boiling, you have two phases present. During the melting, you have solid and liquid together, and during the boiling, you have liquid and gas together. But through all these slope sections, you only have one phase present, whether it be just the solid, just the water, just the gas, in which case each one of those is going to increase their temperature as you increase the energy. So the temperature remains constant during a phase change. So let's walk across. During the ice solid stage, the molecules are vibrating. They're vibrating more and more, but they still have not broken free of their organization, so they do not have enough energy to become anything else until they get to the melting point. When they get to the melting point, now some of the molecules get enough energy to break free and become those liquid molecules, but not all. You keep adding until all of the solids become liquids. And then once it's a liquid only, you add water and you add heat, and the water becomes more and more agitated, gets more and more kinetic energy, and gets hotter and hotter and hotter. It doesn't change phases yet, it just gets hotter and hotter and hotter. As we would have a flask on a hot plate. It would get warmer and warmer and warmer. You'd have some condensation there, but it wouldn't be boiling until it gets to the boiling point. And then once it gets to the boiling point, all the energy you put into it is going to go towards changing those liquid molecules into gas molecules, and the temperature increase stops. All the energy that goes in is going towards making the liquid molecules become gas molecules, and the temperature stays constant. And then finally, once it's all gas, you're just going to keep adding energy to it. It's going to be getting hotter and hotter and hotter. Now, there are some weird exceptions, and the one that you is always given as an example of the weird exception is sublimation or dry ice. You may have seen demonstrations with dry ice. Dry ice is called dry ice because it goes from a solid to a gas without entering the liquid phase. It's never wet. It's never liquid. So hence the term dry ice. It goes straight from solid to gas. That's sublimation. Sometimes, in order to make dry ice, you have to compress it enough and make it cold enough that it'll go straight from gas to solid. That's called deposition. So to wrap this up, one of the reasons why we worry about temperature changes and phase changes is the temperature of the water in nature. So, question. So we've had temperatures around here that have definitely been below 32 degrees Fahrenheit. We've actually had times where it's been below zero you wouldn't believe it today because right now it's probably in the middle 70s as I videotape this, but we've definitely had temperatures below 0 degrees Fahrenheit. Very, very, very cold. Yet, our Chesapeake Bay, which is absolutely full of water, does not freeze solid when the temperature outside is less than 32 degrees. Why do you think that is? Well, let me enlighten you. A couple cool things about water. Okay, a couple cool things about water. One, first off, the Chesapeake Bay at 32 degrees would not freeze. The main reason the Chesapeake Bay would not freeze at 32 degrees is because the Chesapeake Bay is brackish, like we said in one of our previous videos. It has some salt in it. So the fact that it has salt in it allows it to be freeze at a lower temperature. Okay, so maybe 20 degrees. So why on those temperatures, days when it's way below zero, does the Chesapeake Bay not freeze? Well, the other cool thing, water is weird. Water is weird. Water is super odd, and it does one really phenomenally cool thing that no other substance that I know of does. And that's the fact that water, when it becomes a solid, it is less dense than its liquid. All other materials I can think of, when they freeze, they become more dense. They get closer together. The molecules get closer together as they rearrange themselves in a more organized way. Water doesn't. Water goes the other way around. So why is that significant? Well, let's think about it. If water were to freeze, just like everything else, you would have this layer of ice on the top of the water. It would be more dense than the water and fall to the bottom. And it would keep freezing and falling and freezing and falling and freezing and falling, and the Chesapeake Bay would fill up with ice from the bottom up. But you've probably all seen a frozen pond or a frozen lake or maybe even a frozen puddle. Where does the ice sit in a frozen puddle or a frozen pond? It sits on top. So what happens is the ice sits on top and forms a layer of, in some cases, a very thick layer. Up in the Arctic, the layer will be as much as 3-4 feet thick across lakes. That's why they can drive across lakes. If you've ever seen the TV show Ice Road Truckers, they drive across lakes because the lakes have 3-4 feet of ice, but it's on top and underneath, now no longer exposed to the cold temperatures outside, is the water. So the water, the layer on top, actually provides a insulation, a physical barrier from the very cold elements to the water, so the water doesn't freeze all the way down. Okay, solubility, the salt in the water keeps it from freezing, but also the fact that water is really, really weird, and water, when it does freeze, it freezes from the top down. That's absolutely backwards. Okay, so anyway, there's your little nugget for the day. Hopefully everybody's staying safe and healthy, practicing your social distancing. We're wrapping this year up. We will see you on the next video. Toodles.